For section 3.3, we'll be defining the trigonometric functions for the third time this semester. Right? So here's what we've had so far. All right, the trig functions defined. First, using triangles. In fact, right triangles. I should be explicit about that. Using the right triangle definitions. We had SOHCAHTOA and the reciprocal identities as well. Okay, so opposite, adjacent, and hypotenuse sides of right triangles. The second time we did it with coordinates. That's where we had x and y coordinates and r, the radius. Okay. Now the third definition right here is where we are going to be using arc length. Arc length t, where t is the arc length specifically in the unit circle. Recall that the unit circle is always defined so that the radius is equal to 1 unit of measure. Okay, so a circle of radius 1 foot, or a radius 1 centimeter, or a radius of 1 mile, for example, would be considered a unit circle in all those examples. Anytime that we are in the unit circle, we're going to call the distance traveled along a circular arc, the arc length, we're going to call that t. T is the variable that we'll use if we are talking about arc length in the unit circle. If it's not the unit circle, we use s for the arc length. Okay, so let's make a note of that. I've said this before, but we'll be saying it again. Okay, s is the variable that we use for arc length. In general, okay, that is for any value of r. Okay, but t is specifically the variable for arc length if r is equal to 1. That is when we're in the unit circle. So if we go back to the definitions that we already had for the trigonometric functions using the coordinates, okay, we can just replace theta with t anytime that r is equal to 1. Okay, so recall when we are using x, y, and r, we already had defined, for instance, that the sine of theta is equal to y over r, and that the cosine of theta is equal to x over r, and that the tangent of theta is equal to y over x. Then we also had that the cosecant of theta was equal to r over y. The secant of theta is r over x, and the cotangent of theta is x over y. Okay, so we already had this from before. Okay. Now, if we are in the unit circle, then r is specifically equal to 1. And by definition, theta would equal t, okay, if theta is measured in radians. Okay, we already stated this when we introduced the radian unit of measure, right? The definition of the radian, okay, the definition of the radian is that theta is equal to s over r, okay, if theta is being measured in radians. Notice that this equation becomes theta is equal to t if r happens to equal 1, right? If you plug 1 in for the value of r, then theta is just equal to s. And any time that r is equal to 1, we use t for the arc length instead of s. So it is always going to be true that theta and t are equal to each other numerically, as long as theta is measured in radians. So if we go back to these definitions that we already have created previously, which work for any value of r, okay, if we make the following changes, if we are in the unit circle, that is if r is equal to 1, then theta, the angle, is equal to t, the arc length in the unit circle. So we can replace theta with t if we replace r with 1. Right? If we replace r with 1, then we replace theta with t, then this definition becomes the sine of t is equal to y. Because r would be equal to 1 at the instant we replace theta with t. Right? They both are getting replaced simultaneously. Right? So if r is equal to 1 and theta is equal to t, then we get the sine of t equals y over 1. In other words, the sine of t is equal to y. Similarly, if we replace theta with t and r with 1 simultaneously here, the cosine of t is then equal to x. Notice there's no r in the tangent equation, so it's still true that the tangent of theta is equal to y over x. Okay? And as before, that's under the assumption that x is not equal to 0, otherwise this would be undefined. If we replace r with 1 and theta with t, then we get that the cosecant of t, go back here a second, right? The tangent of t, it's the point, right? The tangent of t is equal to y over x. We've just changed the variable, right? We're just saying if the argument is no longer the angle, what if the argument was a distance? In other words, what if we didn't know the rotation, but what if we knew the distance an object traveled, like along an orbit or along some kind of a circular path? If we knew how far it moved, could we still evaluate the trigonometric functions, even though we don't yet know the angle? And the answer is yes, as long as we consider where the angle and the distance are equal to each other in measure, which would be under the assumption that the angle would have been in radians if we did so, okay, then we can define the trigonometric functions in terms of the distance the object traveled along a circle with radius 1 unit. The cosecant of theta, the cosecant of theta is r over y, so the cosecant of t would have to be 1 over y, as long as y is not equal to 0. Right? The whole point is that when we use the variable t for arc length, we are saying that r would have to equal 1 simultaneously, because t is the arc length in the unit circle specifically. Okay. The secant of t is equal to 1 over x, as long as x is not 0, otherwise it would be undefined. And the cotangent of t is equal to x over y. There's no r incorporated in the cotangent formula, and that exists as long as y is not equal to 0. So here are the new definitions, the third definitions of the trigonometric functions. They are all with respect to an argument that is a distance. Okay? So the input to the trigonometric functions is no longer required to be an angle. Now the input can be a distance. That is the point. So the input is now a distance. And in fact is a distance along the unit circle. Okay? In standard position, by the way. So we've now redefined the trigonometric functions, okay, in terms of this variable t as the input. So t represents the distance traveled along the circle. T, therefore, can be any number from negative infinity to positive infinity. Just consider an object that starts here at the initial point 1, 0 and starts traveling in the counterclockwise direction. Even if it were to rotate a whole lot of times, we would be able to find a value t that would be the distance the object had traveled. So if the object travels through one rotation, it would have gone 2 pi units of distance, because the circumference is 2 pi, when we are dealing with a unit circle. If we went through 2 rotations, it would have gone 4 pi, which is about, 4 pi is about, 12.6, about 12.6 units of distance. If it would have traveled, let's say, 10 times, 10 complete cycles around the circle in the positive direction, then we would say that the distance it had traveled would have been 20 pi units of distance. Let's say the radius was equal to 1 meter. 10 times around the circle would be 20 pi meters of distance. That's about 63 meters of distance it would have traveled. And that would be associated also with 20 pi radians of rotation, which you can convert into degrees. So we could talk about how many degrees of rotation as 360 times 10 is 3,600 degrees. So an object that would have gone through 3,600 degrees of rotation would have traveled a distance in the unit circle of 20 pi, or approximately 63 units of distance. So it's possible for t to be however large we want it to be. It's just to say that we're just traveling larger and larger distances. It's also possible for t to be as large but negative as we might want. That would just say that we're traveling a large amount of distance but in the clockwise direction. Okay, we are rotating clockwise, but now we're talking about the distance we would have traveled instead. Okay. The domains for the tangent and the secant. Okay, notice that the tangent and the secant, we already said, are not going to exist whenever x is equal to 0. That is, if we have a quadrantal angle, if we terminate on the y-axis. Anywhere we would terminate on the y-axis. Well, that means that tangent and secant are not defined at values like pi over 2. Pi over 2 would be the positive y-axis. Or values like 3 pi over 2. Okay, 3 pi over 2. If k is an integer, is the number 0 plus minus 1 plus minus 2 plus minus 3, for example. Right? If we took that, let's say k is equal to 1, then the expression pi over 2 plus k pi would be pi over 2 plus 1 times pi. What's pi over 2 plus pi? It is 3 pi over 2. In other words, this is saying this expression implies that any time that you choose an integer, k, okay, and plug it into this formula, pi over 2 plus k pi, you will end up at either the positive y-axis or the negative y-axis for any value, for any integer k that you select. So these are going to be all the places whereby tangent and secant would be undefined, for example. Similarly, because we said that cotangent and cosecant would be undefined anytime where y is equal to 0, that is, anytime where we end up on the x-axis, okay, then the domain of the cotangent and the cosecant function, they would be defined in terms of t for any value of t except a value of t that would terminate on the x-axis. Values of t that would terminate on the x-axis would be values like pi, and also negative pi, right? As well as 2 pi, which would be a full rotation back to the positive x-axis, as well as negative 2 pi, a full rotation in the clockwise direction, okay? Or any other integer multiple of pi, like for instance 10 pi, or 20 pi, or 15 pi. Okay, which would always end up terminating, a multiple of pi will always end up terminating on the x-axis then. Okay, if it's a value of t and it is a multiple of pi, will end up on the x-axis. And on the x-axis, the y-coordinate is 0. So for any value of t that is an integer multiple of pi, the trigonometric functions cotangent and cosecant would therefore be undefined there. The ranges of the circular functions. Okay, the ranges are the outputs of the trigonometric functions. Consider that by these definitions right here, right, in the unit circle, the cosine is just the x-coordinate of the terminal point. Right? The terminal point has coordinates x, y. The x-coordinate is the cosine of t. the y-coordinate is the sine of t. This is consistent with the definitions we already had for the trigonometric functions. Just when we're using t, we are saying that r must equal 1, right? And x and y, as they were previously, x and y are the coordinates of the terminal point. We just don't need to solve for r now if we are using t, because we already know what r is equal to if we're using t. R must be 1 if we're using t. So if cosine is the x-coordinate and sine is the y-coordinate, then just by looking at the circle itself, the unit circle itself, we can see that there are bounds on the cosine and the sine. Right? What's the largest possible x value that can be attained at any point along the circle? If it's the unit circle, the largest that x can get is at this point right here. That's as far to the right along this x-axis that we can go. And that would be x equals 1. So if x is never more than 1 in the unit circle, then the cosine of t can never be more than 1, because the cosine of t is what x is equal to. So notice that, right, x is always between -1 and +1 if we're on the unit circle. Always between -1 and +1, the x-coordinate for any point we choose. Okay, along this circle. Always an x value between -1 and +1. Therefore, the cosine must be bound between -1 and +1 as well. Similar argument for the y-coordinate in the sine function. The y-coordinate for any point on the unit circle is always going to be between -1 and +1. Therefore, by definition, the sine of t would have to be between -1 and +1. No matter how large t is selected to be, we are always going to end up at some point along this circle, and the associated x-coordinate and y-coordinate will always be bounded between -1 and +1. Therefore, the sine of t and the cosine of t have a range from -1 to +1. Those brackets include -1 and +1 as possible values as well. Okay, now at this stage in our analysis of the trigonometric functions and in defining them, okay, it is probably best to have maybe a note card or a review sheet whereby you have these definitions and these domains and ranges written out until such point comes whereby you've either memorized these so that you start to own this information, okay, or after you do enough exercises using this information whereby it starts to sink in where you no longer need the review notes with you. Okay, so I would have, a note sheet, maybe principally have a note sheet with things like the right triangle definitions and SOHCAHTOA until such point where you're comfortable with those, where you don't need those notes anymore. As well as for the coordinate definitions with x, y, and r, have that nearby, along with r squared is equal to x squared plus y squared, until you reach a level of comfort with that information that you no longer need the review notes with you. And similarly, this information here, until you reach a point where you where you can recall this information, okay, more comfortably, more confidently. Okay. Until such point, I would say have this information nearby so that you can continue to use it. All right. Now we can answer conceptual questions using the unit circle. One of the principal questions we can be able to answer using the unit circle is going to be associating, when we are given the unit circle specifically, associating the coordinates of a point along the unit circle with the trigonometric functions. Okay. So let's take a look at an example like that. I have an example from the notes. Let's take a look at an example from our notes here. Right. So I have some worked out for you already in the notes. All right. I go through the definitions. I go through like demonstrating why the domain and the range are as they are in the notes. If you want to review that, okay, you can. And that's what it's there for. Okay. Well, let's take a look at some examples. Here's an example right here. Okay. Find the coordinates of the terminal point xy if the unit circle, okay, in the unit circle, if t is equal to 4. Round results to 3 decimal places. Interpret this then geometrically. Let's interpret that geometrically. We are told we are in the unit circle and we are given t is equal to 4. Our interpretation of that, therefore, is that this 4 is the distance we have traveled along the arc of the unit circle, starting at the initial point 1, 0. So I can already envision a picture of this situation right here. I want to envision the unit circle and envision traveling through that unit circle from the initial point 1, 0 in the positive direction, a distance of 4 units. Now, what quadrant might that put us in? All right. If t is equal to 4, find the coordinates x and y. Okay, let's draw a picture. Okay, so the unit circle, right, let's say that's the unit circle. It's hard for me to draw a circle on this thing. Okay, let's say that this is the unit circle. If this is the unit circle, then it has points on it like 1, 0. Because that would be exactly a distance of 1 unit from the center. And points like over here would be negative 1, 0, another point that is exactly 1 unit from the center. And this would be point 0, 1, and the point 0, negative 1. This is the unit circle. That is where r is equal to 1. It has to be the unit circle if we're given a value of t, because t is the arc length specifically in a unit circle. Notice that 4 is greater than 3.14, right? That is, it's greater than pi. Okay? But it's less than 3 pi over 2, in fact. Okay? What is 3 pi over 2? Right, approximately, what, 4.7. Okay, 4.7. So, yeah, certainly 4 is between 3.14 and 4.7, so we're somewhere in quadrant 3, therefore. Okay, so if t is equal to 4, okay, that means we are somewhere in quadrant 3. Okay, this would be the angle theta right here. Okay, this is the distance t right here. Okay, and recall that theta is equal to t. Okay, so that means that we have an angle theta that is equal to 4 radians. Okay, so theta is equal to 4 radians, and t is equal to 4 units of distance. Right? They both have the same numerical value. But theta is the label I'm giving to the angle. T is the label I'm giving to the distance that this object traveled along the unit circle. And this puts us in quadrant 3. And in quadrant 3, we expect the x-coordinate to be negative and the y-coordinate to be negative as well. Now, how can we find the x-coordinate and the y-coordinate? By the definition. Okay, by the definition of the trigonometric functions, the cosine of t is equal to x, the sine of t is equal to y, and we're given the value of t. So therefore, these 3 dots means therefore, okay, therefore x in our case is equal to the cosine of 4, and y is equal to the sine of 4. Now, when you go to your calculator to evaluate this, make sure that you are in radian mode on your calculator. Check to see that you're in radian mode, not degree mode. This is not 4 degrees and 4 degrees here. If it was 4 degrees, we would write degree symbol. It is a unitless measure. And although it was given to us as a distance, 4 is a distance, okay, we build the radian measure for an angle so that the number we use in radians is always exactly the same as the number we use for the distance in the unit circle. So we can go to the calculator and we can plug in cosine of 4. As long as we're in radian mode, it would evaluate this. It would evaluate this correctly. Whenever you use the radian mode in the calculator, the input as far as the calculator is concerned, is the same whether it was an angle or a distance. Right now we're plugging in a distance, okay, 4 units of distance, okay, which is done by using the radian mode on the calculator. Okay, so the cosine of 4, and we're going to want to round that to a certain number of decimal places. What did I say in the worksheet here? Let's round to 3 decimal places. Okay, you should see these numbers come up from your calculator now. Right, the cosine of 4, if you are in radians, I get negative 0.6536436,209, and that rounds to negative 0.654, for example. Okay, so cosine of 4 is approximately that, negative 0.6536436,209. And the sine of 4, that's the sine of 4 radians, or the sine of 4 units of measure, units of distance along a circular arc, is negative 0.7568024953. Okay, so we want to round those to 3 decimal places. X is approximately negative 0.654, and Y is approximately negative 0.757. Okay, so geometrically then that means that the coordinates of this point right here, the coordinates x, y, okay, would be these. Okay, the terminal point on the unit circle when t is equal to 4 is the point with coordinates x, y, where it's approximately negative 0.654, comma, negative 0.757. Okay, so by this new definition of the trigonometric functions, we are able to associate the coordinates of a terminal point to the distance that was traveled along the circular path. Okay, so now let's take a look at this example right here. If t is the distance along the unit circle from the initial point 1, 0 to a point with coordinates 0.25, negative 0.968, determine all 6 trigonometric functions of t. Round to 3 decimal places. Let's interpret this geometrically. That is, let's draw a picture that represents this situation. We are in the unit circle, which we must be in the unit circle if t is being used for the distance. But it's told we're in the unit circle. We start at the initial point 1, 0, and then we travel to the point with these coordinates x, y. Notice that, first of all, that x and y have to satisfy the equation of the unit circle. That is, that x squared plus y squared would have to equal 1. So x and y are not just arbitrarily chosen quantities. It has to be that the square of x plus the square of y is equal to 1 because we're in the unit circle. Also, notice that both the x value and the y value are between negative 1 and positive 1. This must be true to be in the unit circle because you can never be more than 1 unit away from the center, and the center is the origin. So, now let's draw a picture representing this situation here so we can visualize this. So we have the unit circle, and we have t is the distance, okay, along the unit circle from the point 1, 0 to the point with coordinates 0.25, negative 0.968. Okay, so try and draw a unit circle here. Okay, let's pretend that's the unit circle. And then this is our initial point right here. That's 1, 0. Of course, that is along the positive x-axis. Okay, here's the positive y-axis in this direction. Let's see, what quadrant would this put us in, by the way? Okay. This point has coordinates where the x-coordinate is positive and the y-coordinate is negative, so that would be a quadrant 4 point. Notice the y value is very close to negative 1. Okay, so I expect this point to be far down on the unit circle, right? Not quite. Here's where -1 would be in the y value, for the y value. So this is approximately -1, right? But it's in quadrant 4 where the x value is positive. Okay, so here would be a terminal side. Right, this would be a terminal side. And the angle of rotation would have been this angle right here. That would be our theta. And if theta was measured in radians, then theta is going to be exact number equal to t, where t is the distance. And we're focused on distance right now. So t, I'll put this in orange now, okay, starts here, okay, and is the distance, right, the distance represented by this orange arc. Let's try that again. Okay, so t is this distance from 1, 0 to that point. It is in the positive direction because, well, right now I've chosen t to be in the positive direction. In fact, t could be any distance along the circular path that would have ended up at this point. So for instance, I could have chosen t to be a negative number that was this distance right here. That would have been okay. We could have even chosen t so that we went through the circle multiple times, as long as we end up at this point right here. So there's actually many different values of t which we can say are coterminal. They end at the same point. So this is one possible value of t that would be associated with this terminal point. Okay, but regardless of which t we choose, as long as we end up at that point, the trigonometric functions for that t are always going to end up to be the same quantities. By the periodicity of the trigonometric functions, that would be true. Now the coordinates of this terminal point should be 0.25, -0.968. We are in the unit circle. Remember that in the unit circle, theta and t are equal to each other. That's where theta is a measurement of the angle in radians and t is the arc length. This is always true in the unit circle, and it requires that theta is in radians for it to be true. So, if we wanted to say find out what is the sine of t, it's the same as us saying what is the sine of theta. It means the same thing as long as theta is in radians and we are in the unit circle. By the definition we have for this section, the sine of t is equal to the y coordinate of the terminal point. So without having to go to the calculator or anything, we just take the y value, and that is the sine of t, no matter what t happens to be. So the sine of t is -0.968 by definition of the sine function with respect to arc length. The cosine of t by definition is equal to the x-coordinate, so the cosine of t is just 0.25. The tangent of t is defined to be y divided by x, so that is the sine of t divided by the cosine of t. So we take the sine of t, or the y-coordinate, and we divide it by the cosine of t, or the x-coordinate. Okay, and then we go to the calculator and we get an approximation for that. -0.968 divided by +0.25, I'm getting approximately -3.872 is the tangent of t. We still don't know what t is, and we weren't asked to find out what t is. Okay? But we are finding the trigonometric functions of t. All right. Using the reciprocal identities, we can solve for the remaining 3 trigonometric functions as well. All right. The cosecant of t is 1 over the sine of t, or 1 over y. All right. It's 1 over y, or 1 over the sine of t. Okay. So 1 over -0.968. Okay, we'll approximate that to 3 decimal places. And I'm getting that's approximately -1.033 for the cosecant of t. All right. The secant of t would be 1 over x, or 1 over the cosine of t. That's 1 over 0.25, and that just equals 4. And finally, the cotangent of t can be found by taking x over y, or cosine of t over sine of t, or the reciprocal of the tangent of t. All right, in any of those cases, all right, for instance, let's take 0.25 divided by negative 0.968, and then approximate that to 3 decimal places of accuracy. I get negative 0.258 for the cotangent of t. Okay, check those answers with the notes. Right? That's how we're finding those quantities. We did not find t in any case. As is the usual approach we can take in trigonometry, we can visualize this, so we can use a geometric sense to try to interpret this. So I drew a picture of the unit circle. I labeled the initial point and the terminal point. I labeled the distance t at one possible distance t. That is a distance along the circle that goes from the starting point to the ending point, the initial point to the terminal point. That would be labeled as t. I even associate it with a central angle of theta as a reminder that these two quantities are equal to each other in value as long as theta is in radians. And then using our definitions for the trigonometric functions, which really are the same definitions we had when we were talking about the sine of theta and the cosine of theta and the tangent of theta. It's the same definitions we had there, and with now, since we're using t as the input, it means that r is always going to equal 1. Okay, so get some practice with using this new definition of the trigonometric function so that we can continue to get used to using distance, that is arc length, the length along a circular arc, as the input to trigonometric functions. We can now start examining more application problems whereby the input is either a distance as opposed to an angle, or simply just a number. That is a number that is unitless. We can now evaluate the trigonometric functions where the input is just a number that has no units associated with it. Our interpretation of a unitless input to a trigonometric function would be as either a radian measured angle, or an arc length along the unit circle. But nonetheless, we can now evaluate the trigonometric functions where the input has no units. Any time that you are using a unitless measure as the input to a trigonometric function, if you're going to your calculator, you should set it to the radian mode, not the degree mode. And if you just want to exclusively use degrees, if that's what you want to stick with for the time being, then you need to convert these unitless inputs, whether they are distances or radian measures of angles. You're going to need to convert them into degrees and then be prepared to convert them back into radian or unitless measures later in order to answer the questions as well, depending on what the questions are asking. So get some practice with these types of exercises on the homework and let me know if you have any questions on that. Okay, take care.